is on solar systems. And so you can join us on February the 24th for that. And obviously you got an email about this one, so you'll be getting an email about that one. Welcome, everybody. And with that, I'm going to turn it over to Lauren Isom to talk about ethanol engines in our first Bioenergy Fridays web seminar of 2012.
Good morning. I'm Lauren Isom with the Industrial Agricultural Product Center at the University of Nebraska. Been working with the center for over 10 years now, and the center was established in 1988, actually, to look at value-added processing for new uses of Nebraska's and the Midwest regions and agriculture commodities. And one of those key issues has been biofuel. So that's been an area that I've worked on and we'll share some information about today then. Okay. So I would like to just give a brief outline here of what I plan to discuss today, and we'll start out talking about why alternative energy sources are important, different types of alternative energy sources. We'll review some of the emission standards, as that has a major effect in and why they may be adopted. And then we'll dig into some recent research we've done over the past 3 years with the Water, Energy, and Agriculture Initiative. And specifically, that'll look at ethanol for spark ignition engines and ethanol fumigation over diesel in compression ignition engines. And then we'll wrap it up with a small section on what's in it for you as a producer, I guess, in this case. Okay, so why are alternative energy sources important? One of the more obvious reasons would be the renewable domestic source, ours. They also have the potential to reduce emissions, and that's important with existing regulations or maybe future regulations that monitor greenhouse gases, and meeting an engine compliance and such as Tier 4 for a compression ignition and system. The other reason would be fluctuation of petroleum prices and petroleum supplies. So that's just one other reason to look at that. Specifically, if you're looking at irrigation and product for commodity crops, then if you would have an energy source that's tied to that commodity, it may be advantageous compared to something that's a petroleum-based product that may see spikes when your commodity prices don't raise. Now here recently, commodity prices have been tied much closer to energy prices due to the development of biofuels, so that's becoming a little bit less of an issue. But then specifically for the research project we were also looking at the limitations of electrical load and price adjustments at peak demand. And so if a producer was irrigating their crop with electricity, on the hottest days of the year, those are also the days that have the highest demand for residential and industrial cooling, and so the production applications may be limited on how much electricity they can use or the ability to irrigate their crops on the hottest days of the year. So that is a concern that some of the producers have, as well as the power generator. They're concerned about having capacity for people, or in some cases where they would have excess load and put limitations on their system. As far as different sources to consider, or if you review literature and things, many options have been presented, anything from wind to ammonia. And I listed those two as two that I find interesting, because when we think of it for crop production, I would rather be using the ammonia to feed the crop, and if I'm concerned about using electricity because I might not be able to produce on some of the hottest days, I would be a little concerned with wind as well, and that I might have to wait for the wind to blow in order to irrigate my crop. So lots of alternatives are out there. Here at the Industrial Ag Product Center, we've looked at refined vegetable oils and tallows. We've also looked at the biodiesels from those feedstocks. We did some research in the past that looked at ethanol and biodiesel blends. This would be more along the lines of e-diesel, or in the study that we did, we looked at at EB diesel. And then we've also did studies with flex fuel vehicles on the ethanol use of those various fuel blends as well. Currently, we're looking at research with ethanol for spark ignition engines, and then the fumigation of ethanol over the diesel into the compression ignition engine, and then hydrated ethanol as a source as well. So we'll get into some of that here, but I'll give a little bit of background information on why we looked at the irrigation industry here in Nebraska. That's that there's roughly 80,000 to 100,000 irrigation irrigation wells in the state of Nebraska for agriculture, and about well over half of those are powered by electricity, but over a quarter of them are powered by diesel fuel, and then the remainder are either natural gas, propane, or gasoline. And the section for gasoline and gasohol, according to a 2008 study, is very small. It was less than 1%. Since then, we have had a company here in Nebraska, AmeriFuels Energy Solutions, and they estimate that they've placed around 200 engines in Nebraska and Kansas that are modified to burn ethanol, or combinations of ethanol and natural gas in a lot of cases. The other thing that's not denoted in this chart is some of the diesel fuel could be biodiesel. That's not going to show up in these studies, but biodiesel or biodiesel blends would work in the diesel fuel category as well. Looking at the irrigation and wells that are registered in Nebraska, this here graph here just gives an illustration very quickly of how rapid the growth has been over the years, and where we're at in adopting more and more of those irrigation systems. And then if over half of those are going to be still continue to use electricity, then that's an issue for the power producers. So, I'll talk a little bit about emissions, and that's it. Emissions are regulated by the mass per energy produced. So if we think of this in the transportation energy, it's the mass of emissions and per mile down the road. In stationary applications, it's either in grams of emissions per horsepower hour or grams per kilowatt hour. The regulated emissions that we look at are carbon monoxide, and then there's non-methyl hydrocarbons. In some cases, it just looks at the hydrocarbons. Typically, those are the regulations that add those together with nitrous oxide as well. So you have that combination is regulated. And then in the compression ignition engines, we also have regulations on particulate matter. Just as far as some of the standards are laid out, there's different categories. The major differences are whether it's how the fuel is ignited. So you have the spark ignition engines compared to compression ignition. And for example, in the spark ignition, you have new engine manufactured after 2008 are required to meet the newest standards, or engines that were modified after 2006. So there's specifications for what is regulated as far as it's also categorized by application and size. So on the size side, you might have that done by rated engine power, or so how many rated horsepower, or the engine displacement or the cylinder displacement. And then in the applications, you have stationary, off-road, and on-road. There's also other categories such as emergency equipment. But in the stationary example, we'll be talking about for the spark ignition, the limits apply to any point of the operation within the normal range. So in a road application, there might be a drive cycle, and you'd be looking at the emissions over a given drive cycle. In a stationary application, it's within the normal operating range of the engine. I guess a summary on the emissions is that they're complicated to understand and the specific standards. It's not always presented real straightforward. I'm giving an example here for the spark ignition and engines in a stationary application. And just the title alone, Standards of Performance for Stationary Spark Ignition Internal Combustion Engines and National Emission Standards for Hazardous Air Pollutants for Reciprocating Internal Combustion Engines. I mean, the title alone sounds complicated, and then if you know that it's prepared by the Environmental Protection Agency and published in the Federal Register, it just gives you some indication of how complicated understanding it and these documents might be. I did provide the website there if you are wanting to review it in more detail. But in this one here, there's at least a half a dozen to a dozen tables that talk about different situations within the stationary spark ignition engine. So I did a little bit of summarizing here, but first I want to give you a little perspective on what's happened in the last 15 years in this area of regulating emissions. And this is an example from John Deere. They have in one of their brochures that shows the Tier 1 emission regulations for a compression ignition engine. And the boxes are fairly good size here. And this specifically looks at NOx and particulate matter, but that's not the point that I'm trying to make here. Is if you look at the far right of the graph, compare those small little boxes to the full-size boxes at the beginning. Over a 15-year period, we are really tightening down what's allowed to come out of these engines. So that's being a challenge for the engine manufacturers. So I'll give just an example here of the spark ignition engine that we worked with. That is a 8.1 liter GM, so that's producing over 150 horsepower. So that's going to be in this bottom row here, that looks at greater than 225 cc's. On the compression ignition we looked at, that's approximately 150 horsepower engine. So we'll be looking at this set of standards here as well, and the different years. It was actually manufactured in, and I believe it's a Tier 3 engine. So I believe that puts it in the 2008 category. So I'll share a little bit more about the specific project we had with the Water, Energy, and Agriculture Initiative. That's an initiative that is administered through the Nebraska Center for Energy Sciences Research, and it has funding from the Nebraska Public Power District, the Nebraska Corn Board, the Nebraska Soybean Board, and the University of Nebraska Agriculture Research Division. And then this was a 3-year project that we worked on, and its objectives as here are to look at the adoption of biofuel-driven and stationary power units. What we looked at was that the university was getting questions on this, so we wanted to have some experience with these engines, and we could do that through field demonstrations, and we also could evaluate the engines and the fuel delivery systems of those and prepare and give educational presentations in that regard. There was also an interest for us to look at constraints and limitations to the acceptance of this technology and look at the potential impact adoption of these technologies would have. I'm going to look at the project team that we had for that was the Industrial Agricultural Product Center, which is directed by Dr. Milford Hanna, myself, and my partner was Robert Weber, that was the research coordinator. He conducted most of the field demonstration work, Eric, and the in-field testing that we did, as well as analyzed the data. We worked with the Nebraska Tractor Testing Lab, and that's directed by Dr. Roger Hoy, and their staff conducted the in-lab evaluations. And we also partnered with industry in this case to look at different technologies. The spark ignition technology was some technology from AmeriFuels Energy Solutions out of Kearney. And then there, regarding the fumigation, we worked with 2 companies, CleanFlex Power Systems and Camturter here in Lincoln. And then the engines were actually provided either by the industry partners, or in the case of the compression ignition, it was provided by Industrial Irrigations, and then that engine actually was later purchased by the Nebraska Tractor Test Lab. But industrial irrigation set up the original configuration of the engine. So that was done by an external source besides the testing team. The initial objective was twofold, and that was laboratory testing and field demonstrations. So I'll provide some information on what we did in those areas. We compared the power output as well as fuel efficiency. So we looked at things like gallons or pounds of fuel per horsepower hour. We also looked at it on an energy basis, so BTUs per horsepower hour, and then and we did the field demonstrations to look at it at a short-term use. As you know, when we really talk long-term use, we're talking about 1,000 hours of operation, and these applications we were looking at anywhere from 100 to 200 hours in a summer, or was the applications we looked at. We did compare the emissions. We did that with a 5-gas analyzer. So if you reference EPA standards, our equipment wasn't sophisticated enough to meet their standards, but it provided information and data that was a good indicator of where these things would be as far as an emission profile standpoint. And we were able to use that information lots of times from the 5-gas analyzer. It would come out as a percent of the exhaust stream or in parts per million. So we could use that data and do calculations to estimate the emissions on a grams per horsepower hour basis. So as far as the spark ignition engine, I think I referenced earlier that we used an 8.1 liter GM engine, and for that work, it has a continuous horsepower rating between 90 and 135 horsepower. It was provided by AmeriFuels Energy Solutions, and the base test that we did in the lab was with liquid propane, and then in the field we actually did work with natural gas to where we could do combinations of dual fuel applications and in the field as well. So the technology provided by AmeriFuels was electronic fuel injection, and as well as a complete, it added the fuel rail to the system, so it was a complete engine, and that they would sell and market. It wasn't an aftermarket product, and it would allow total fuel replacement, or you could use it in the dual fuel application as I referenced. There's a photograph of that engine in the laboratory, just as it was set up to do the lab testing. And highlight some of the findings here, and then we'll look at some of the data from this test. But when we compared it to the ethanol operation to the LP gas, as when it was burning on ethanol, it increased power output per energy consumed. It dramatically reduced the carbon dioxide and the carbon monoxide emissions, and it shows the potential to reduce the hydrocarbons and nitrous oxide emissions. The one point and I want to reference here is that it did lower the energy consumption, but less BTUs per hour is not specifically a lower operating cost. You have to, when we're talking about economics, then you have combination of the engine efficiency as well as the energy cost for the fuel. So we'll talk some more about that towards the end of the presentation. In the field demonstrations, that's at the engine and the fuels performed very well, gave no indications of engine wear or beyond the normal break-in procedures, and no concerns for the operators. The farm managers didn't have any complications with the operation of the engine. Looking at some of the data that we had from this study in the lab, this one looks at energy consumption, and I will first highlight just here a little bit. The propane is represented in the triangles, and the ethanol is represented in circles. If it's colored, it was 75% of load, and if it's an open circle or triangle, it was at 90% of the load. So that allowed us to look at the operating range that is typically seen in an irrigation practice, that you're going to load these somewhere between that 75 to 90% load. and at various engine end speeds across the bottom of the graph here, and then BTUs per horsepower hour is what we looked at. So you can see, as I highlighted earlier, that we used less BTUs to produce a horsepower when the ethanol fuel was used than in the propane situation. On the emission side, we looked at carbon dioxide, and you can and see that this is these data points are pretty much grouped at below the circles of, or the ethanol is that typically produce less grams of carbon dioxide per horsepower hour. On the carbon monoxide, you saw a similar situation, and in that case, and carbon monoxide is one of the limited factors. So we do have here that the approximate at a emission standard is down here in this lower 4 grams per horsepower hour. Hydrocarbons, and again, you can look at the data wasn't quite as clear here, but we tend to see that the ethanol performed it by having some lower, at least than these points up here where the propane seemed to get a little high, but hydrocarbons aren't really as critical an issue because that's usually combined with nitrous oxide, and in comparison, nitrous oxide is the more critical issue to control. And here again, you can see the different data points that show the circles are ethanol and the triangles are the propane. So some of the things that we looked at from the field demonstration side of this engine, in 2009 we placed this as engine out at the Southwest Research Farm near Curtis, Nebraska. It operated for 95 hours and consumed 970 gallons of denatured ethanol, and it pumped 7.8 million gallons of water. I'm not exactly sure how many acre inches that was for that operation, but that's just kind of a outline of what it did in that season. In 2010, we set it up to do a lot of field testing, so it was demonstrated, but we did some testing with the dual fuel applications for denatured ethanol and natural gas combinations. And then this past year, it was at the Clay Center site again, and it operated on a set rate of natural gas and ethanol, operating for 280 hours, consuming 560 gallons of denatured ethanol and 212,000 cubic feet of natural gas. An interesting point with the dual fuel approach is that sometimes in the use of natural gas, or if people have the opportunity to have wellhead gas, which is typically priced at very low prices, as they have the opportunity to add energy into that system if for some reason the line pressure is low or the energy content of the gas would drop off on wellhead gas. It's not always real consistent. So you can supplement that with ethanol fuel in the same engine and get maximum pumping or meet your pumping demand, where in some cases without ethanol, they would just have to back off the amount of water they could produce, and then their system wouldn't operate as efficiently, or their irrigation process wouldn't work as well for them. But with this dual fuel approach, they were able to maintain water pumping capacities. As far as the compression ignition goes, we'll review that a little bit. We worked with a John Deere 4045H. It's a 4.5 liter engine, and we had two baselines that we looked at. We looked at a baseline with number 2 diesel, and we also looked at a baseline with B5 soy biodiesel. So those are our two baselines and that we evaluated against. And the biodiesel really performed at the same level. Again, it was only a 5% inclusion rate, but it really performed significantly with no significant differences in the fuel output. So a lot of the graphs don't actually represent the biodiesel on the graph. But this is an example of the engine set up in the laboratory testing lab here. Some of the different tests that we conducted, the CleanFlex power system, fumigated hydrated ethanol, 120 proof prior to the intake manifold, and it used a computer-controlled injection spray nozzle. This injection was after the turbo but before the intercooler. On the cam turret technology, it was a similar process using 120 proof denatured ethanol and water, and it was prior to the turbo and the intercooler. And they used a different atomization nozzle that operated at very low pressures. Both of the systems are dual fuel systems. They substituted approximately 20% of the energy that was traditionally provided by diesel fuel, and they also used the diesel fuel as the ignition source. So there wasn't no spark ignition was added to these diesel engines. It was just using the compression of the diesel to ignite the entire fuel source. And in this case, these were either installed on existing systems, so this could have been an aftermarket application. Some of the findings we had there was that the hydrated ethanol, when we compared that to diesel only, it lowers the energy requirement, so less BTUs per horsepower hour were used in that scenario. It did increase the carbon monoxide and the hydrocarbon emission levels, but it also lowered the nitrous oxide emissions. So in those cases, we had a benefit on the nitrous oxide side and some concerns on the carbon monoxide and hydrocarbons. And regarding the carbon monoxide and hydrocarbons, we believe that was a result of unburned fuel in the exhaust system. So there's probably opportunities to improve that with atomization and or not nozzle control better or on the injection of it or the quantity of injection at the time. So that's a little bit on the concern with the carbon monoxide. We think that probably can be addressed with some product development, and the advantage being the lower nitrous oxide emissions and the lower energy requirements that, again, and lower BTUs aren't directly related to lower cost. So if we look at the graph here of some of the data, again, on the BTU, it's not quite as clear as it was with the other engine on the spark ignition engine, but it does lower the BTUs per horsepower hour. Similarly, the squares here are the diesel load, and the circles, again, are the fumigated ethanol. All the colored ones are at 75% of load, and the ones that are just open are at 90% load. So the carbon and dioxide here, can't really tell a little bit, but we got it not real significant differences, but a little bit on the carbon dioxide. I'd look at the carbon monoxide. We see that the ethanol tended to be above the emission regulations. And on the hydrocarbon side, we see a similar situation there. And then on the nitrous oxide ones, we see that the ethanol seemed to have lower emissions of the nitrous oxide, but they still exceeded the Tier 4 regulations, which are coming up. That was kind of the target, was could you add technology that would allow you to meet Tier 4 regulations without having to do significant modifications to the engine. That's a pretty tight regulation to meet, and in this case, we weren't hitting that with the diesel alone clearly, and the ethanol fumigation didn't get it as low enough either. There was also some additional work done in the ethanol fumigation side. A graduate student here, Grant Janosek, did some work with for his master's degree dissertation. And we look here as far as his definition of fumigation was an introduction or the atomization of a liquid into the air intake of an engine. His objectives were to evaluate fumigation and on a basis of thermal efficiency, the emissions, specifically NOx, which is the most difficult to control, and to explore the various concentrations of ethanol mixtures or pure water fumigation. Here's an example of the test setup he had, and this is the same engine that we used in the previous study. We look at thermal efficiencies is in note the side of the graph here is ranges from 35 to 40. So most of this operation was in a pretty tight representation here of 37 to 38.5% thermal efficiency. And thermal efficiency is a measurement of energy in and to energy output. And so we lots of times think of the thermal energy that went into an engine, the BTU rating of the fuel, to the mechanical power output that we had out. So this is typical of what we'd see, even though we can observe some differences as here at different points. The black line is diesel only, and the colored lines are different levels of that ethanol substitution. We had a couple different terms over here. So 100% alcohol by weight is denatured ethanol. 80% alcohol by weight is hydrated ethanol. So it's 80% alcohol, 20% water. And in the 60% and alcohol by weight, that was 60% alcohol, 40% water, or that would relate to 120 proof of ethanol. And then we have replacement rates at 5, 10, and 15%. So that was, if you looked at the diesel operation, we replaced 5% of the BTUs in a 5% replacement rate, and we did that also to a 10 and a 15% replacement rate of the energy content found in the diesel fuel. So we look at nitrous oxide and we average this over all the loads. We have a significant difference in this case that we were able to significantly reduce the nitrous oxide emissions and from this application of fumigation. That was pretty consistent across that if we, this was in parts per million. If we look at it in a similar situation when it's looked at grams per kilowatt hour, you can also see that it's a little bit more dramatic in that effect, that the system does reduce nitrous oxide. As far as the fumigation test procedures, we conducted the test the same as the baseline for diesel-only test, as just as introducing the various rates of water through the air intake. So the water rates, again, I kind of described if it was 6%, and this is a little bit different than the previous data, I guess. It's 6% water because water doesn't have an energy value. We looked at it as a mass flow rate. So in the 6% case, we substituted 6% of the mass flow of the diesel being supplied we supplied at an equivalent amount of water that would have been comparable to 6% of that mass flow rate. So when we look at the data, you see the different categories. We did diesel only, which would be a no water fumigation, and then we added 3% all the way up to 24% of the flow rate of the diesel was fumigated through the air intake as water. So when we look at load requirements, you can see that we were able to maintain load out across that as we added water. It didn't affect the ability of the engine to produce power. The graph here represents different RPMs across the three different bars that are blocked out here. So that's 1450, 1956, and 2203 revolutions per minute. And those are matched up to what we might see in irrigation applications. And again, this is just another look at this, but thermal efficiency, the way we graphed this was as again looking at the water rates across the bottom. The colors of the graph now represent the different engine speeds, and in all cases, as the thermal efficiency was maintained. So adding water in the air intake, basically changing the humidity of the air coming in, had no significant effect on the thermal efficiency of the engine. When we look at nitrous oxide, that's one of the key elements we wanted to look at here. As the water level increased, as we were able to reduce the nitrous oxide emissions on a part per million basis. So some of the conclusions that we drew from this study was that engine power was maintained in both cases, whether it was ethanol, hydrated ethanol, or just straight water. Our thermal efficiency wasn't compromised, so we were able to maintain the thermal efficiency of the engine and the fumigation, and it significantly reduced the nitrous oxide. And in this evaluation, the ethanol fumigation was actually more effective at reducing the nitrous oxide than water alone. Looking at some of the other objectives we wanted to look at for the study of the WE project was constraints and limitations. And one of the concerns brought up was safety with denatured ethanol, and that really wasn't seen as a issue. We talked to a lot of people from the environmental and regulatory side, and as well as transportation side. And the product we're talking about is the same product that is used as coming straight out of the ethanol plants. They have storage procedures and transportation procedures to deliver that product to regional fuel distributors. So delivering those to farmers wouldn't really be a different issue. Handling is always a issue that you want to handle the fuel properly, but it's not significantly different than what you would do for our gasoline. Hydrated ethanol on the other side, we did see as a major constraint, and because it's not commercially available now, and it may require additional regulations if it's going to be traded commercially. The idea of using hydrated ethanol is that if you're in a region that produces ethanol, they have to go through a significant effort to remove the water from the ethanol. They use microsieves, as in the before it hits the microsieve, it's about 120 proof ethanol in a lot of these systems. So there was some interest in if we could pull hydrated ethanol off at that point and consume it, it would be a cheaper product than something that had to see further processing to remove the water content. And in some cases that may be true, but in a lot of these ethanol plants, they've already got the microsieves in place. So the economics of that, actually getting hydrated ethanol at a lower cost, they would have to be studied further, and then you're also increasing the volume and the weight that you have to transport, so it gets back to an energy density issue as well. Some of the other constraints we considered were the capital investment in existing power units. So if you have somebody that's already got an electrical system in place, they've made investments in electrical motors and a power supply line, and so getting them to switch to an alternative, there's going to be some considerations there for capital investment. Similarly, if you have existing engines that are designed for, say, diesel fuel compression ignition and fuel storage systems, changing those systems would incur a event to happen, whether that event is that a naturally occurring event that the engines wore out, or a significant reduction in operating costs or change in scenarios. So from the operating costs, I wanted to look at what is the cheapest source of energy, as well as which system converts that energy most efficiently, and also what systems, what are the labor requirements for the systems? Is it going to require additional labor, or have additional wear components on the engine? So I referenced energy content several times, so we'll look here a little bit at this. We have the energy content represented in kilograms per joule or BTUs per pound, and if you look at diesel is the most concentrated energy source that we looked at. So you compare that. The biodiesel number here, when I was preparing for this, that was the numbers I found. That actually appears a little bit low. Normally we don't see that, but that is B100. The tests we conducted were with B5, so we didn't see this kind of a drop-off with the B5 blend that we evaluated. And on the denatured ethanol, we have a straight denatured ethanol compared to the hydrated ethanol levels we worked at. So if you look at these categories, when we started using the 120 proof ethanol or the 60 ABA, we were about a third of the energy there as the number 2 diesel. So in the cases where we were supplementing in diesel flow, if we would have reduced diesel flow by, say, a 3%, and we would have had to increase the energy content supply with 60% alcohol by weight. That would have been a 9% increase in volume. So that it got into an issue of a lot more volume of liquid fuel going through the engine. So when I try and bring this back down to a little bit of how do you evaluate this, or what's in it for the producer, if you look at the engine efficiencies of these over the range we tested, and again, this was one engine, so most of these tests would be done better evaluated if you looked at a group of engines, but we just looked at one. A thermal efficiencies ranged from 29 to 35%. A typical spot we saw it in the different work we did was 33 or 34% thermal efficiency. On the compression ignition engine and with diesel, it ranged from 36 to 38%. Typical, we'd say, would have been about 37. With the ethanol fumigation, it was really about the same thermal efficiency in that 37, 38% thermal efficiency range. But when you look at the cost of energy, you can, we're pretty familiar with the cost per gallon, and that's at diesel fuel, about $3.38 a gallon, and denatured ethanol at the rack is about $2.31 a gallon. But going back to the energy content and looking at these on a cost per BTU basis, or a million BTU basis is represented here, we see that it's an inverse situation. A diesel fuel is actually cheaper on a million BTUs than the ethanol is. So you'd have to use that situation combined back with a thermal efficiency of an engine, how well that engine converts that energy into mechanical power. So in the compression ignition situation, where it's basically a similar thermal efficiency, whether you fumigate with ethanol or not, there it may make sense to go ahead and fumigate ethanol if the ethanol would cost you less on a BTU basis. So if we had them priced the same, you might decide to fumigate the ethanol in it. If ethanol is higher priced, it may not be economical to fumigate in. If you look at a comparison across the two engines, two technologies, with the spark ignition engine and comparing that to, say, a diesel engine, there you have two things that are working against the ethanol in this case. It's the engine isn't typically showing to be as efficient, and on a cost per BTU basis, the denatured ethanol is actually more expensive for a BTU of ethanol. So you'd have two situations and it's going for you that you'd have to overcome. Some of the things that we also want to consider in that situation, though, is where does the feedstock come from, or where does the energy source come from? And in the case of fossil fuels, we're looking at petroleum oil that's coming from imported sources in many cases, as compared to if we're looking at the biofuels, they're usually produced from a feedstock that's right here in our own backyard. So a local fuel, a domestic resource, and a renewable resource. All right. The other issue that comes into play there is that the renewable energy industry supports the local and national economy and the local and national tax base. So some people will use renewable energy regardless of its economic status just because they want to be supportive of the renewable energy effort and the local domestic production. Bottom line for producers would be to evaluate their current system and their current fuel costs, and then compare that system with the alternatives that we could look at. And with that, I'll conclude the presentation I have here. We did additional work on the field work that I didn't present today, and we also did some additional analysis of this. But I think this keeps us on the time-wise we were talking about, and I'd be glad to answer some questions that people might have.
Thank you, Lauren. There's a couple questions that have come in, but in general, the question is, what are some of these systems commercially available? In particular, I think I'm thinking about the ethanol irrigation engines. Are they commercially available and ready to go for the public? And then how would you, kind of view the progression of people adopting these technologies?
Yeah, the AmeriFuels system is as on a modification of the 8.1 liter GM product, and they are readily marketing those engines, and we know that they have them located in Nebraska and Kansas in a lot of situations. I think they're roughly at that 200 level, unit level of application, and we have heard of some being and located in other regions of the country as well. I saw a video of one operating down in, I believe it was Arkansas, so it's got some distribution outside of the Nebraska-Kansas area, but I know that's the primary area that it's used in and is there. As far as the other two technologies, they're considered at the research stage, so that's why we didn't do the field demonstrations with those particularly, as we are looking at selecting one a system to demonstrate on the farm. We went with the one that's commercially available.
Are all the systems, or these Amerifuel systems, are they dual fuel or are they ethanol only fuel?
They can be set up either way, so they can and put the map they put in there to distribute the fuel can be optimized for an ethanol application or a given dual fuel application. If it's dual fuel, they'll set the engine and to operate on a estimated energy content. If you're going to target 20% of the energy content coming from ethanol, 80% coming from natural gas, they'll set it up a little differently than if you have a situation where you have a very low energy content gas source. Then it might be a set so that you are considering you have, say a reverse situation, 80% ethanol and a 20% natural gas as energy supply.
What kind of modifications are made to these engines to be able to run ethanol?
So in the Amerifuel system, it's primarily a fuel rail is added, as well as an electronic control system to monitor or for the fuel delivery system. So the modification hasn't been a change in the compression ratio. They selected the 8.1 liter engine because it does have a higher compression ratio than some other engines, but they didn't modify the compression ratio of the actual engine. That would be some interesting. We've talked about that as far as future research. That would be an interesting way to look at it is comparing it, because to best utilize the high octane of ethanol, you would like to have a higher compression ratio than these engines are typically set up with. So that's some future research we'd like to conduct.
I saw that a few of the things you did to the diesel engine got it to be under the Tier 4 requirements of the next set of engines. But so what are they doing to engines today to get them into that Tier 4? And I mean, I know kind of the answer, but so what?
Yeah, we could talk a little bit about that. But one of the main approaches to addressing that is exhaust gas recirculation, and in other cases they use a diesel exhaust fluid. And in both cases, in one case you're running the exhaust through the engine, or a portion of the exhaust through the engine, a second time to try and basically get a more complete burn and reduce the level of emissions coming out. In the diesel exhaust fluid, that's necessary for when you have filtering devices, I'll call them, that will capture emissions. Those will build up on in the system, and then periodically the engine has to cycle it and add fuel to that and burn those emissions that ends off of in the case of the filter, I'll call it, or the media that is collecting that. So in both of those cases, as when you add filters, that creates more back pressure on the engine. That can cost you in thermal efficiency of the system. Or if you're having to use a secondary fuel to burn off emission and collections, that's going to increase your cost of operation as well. So it's a real challenge for the engine manufacturers to try and meet these final Tier 4 regulations.
What about the price and the economics? Have you looked at an ethanol to diesel price ratio that would make some of these fumigation things economical? Or so what diesel price does it need to be?
I looked at it there as we talked on that one slide, but as far as the specific price, I don't know that I can say that, but it's you know, if you look at the diesel engine and the fumigation, where it was literally you could maintain the thermal efficiency by fumigating, it would really have to be a situation where you have the fuels, ethanol and diesel, at the same cost, or ethanol being cheaper on a BTU basis. And that's a situation we don't have right now. Back in 2008, it was a situation where ethanol was cheaper on a BTU basis. And I didn't show the information there when we compared it to propane, or the more typical comparison we're seeing is with natural gas. And that the interest in this was highest when, back in 2008, 2007, when natural gas spiked. Right now, natural gas is very cheap on a BTU basis, so that's affected some of the interest in adapting this. If somebody's got natural gas available to them, that's probably going to be the most economical energy source to use.
Great. If there are any questions, type them in now. I did put up a link to a survey in the chat box, and so please click on that link now. It will only take you a minute. It's very short to do that survey, and what we're trying to do in some ways is capture some email addresses in that and ask some real basic questions, so that we can then ask you later how you use this information and things like that, and that'll help us move forward. Also, please, you can, in that survey, you can give us ideas for future seminars and future speakers, and we will be trying to do this once a month, and so any of those speakers would be helpful if you have a good idea or a topic you'd like to hear about. Remember, February the 24th at 10 a.m. is our next one, and our speaker is going to be Dr. Isom from the University of Nebraska, talking about solar cells and new solar PV technology, and that's becoming more and more interesting because solar PV prices have come down, and so that's becoming a really neat renewable energy source to look at. So thank you very much for joining us, and have a wonderful Friday.